All right, everybody. All right. Well, why don't we go ahead and get started? I want to thank everyone for joining our March technical webinar, which is modeling methods for non-ordinary responses. So in other words, some special cases you may run into, or maybe you've already run into, and how you can handle those cases with special tailored models. My name is Martin Beziner. I'm the president and CTO at Staties. And again, my email is right here. So if after the presentation you have any questions or feedback, you can feel free to contact me directly here. So why don't we go ahead and jump right into it. So just our preliminary warning that we always give up. We do have a decent sized group here today. So to prevent any audio disruptions, any screaming babies, any phones going off, we did mute, all attendees are muted. If you have any questions during the webinar, you can go ahead and use the questions feature and go to webinar. I'll try to get through these. I'll try to get to these periodically throughout the webinar, but if I miss one, please go ahead and either email me directly at the email that I gave you, or go ahead and send our entire consulting team an email, stathelp@staties.com, and we'll go ahead and try to answer your question as soon as possible. So there's a couple of ways you can reach out to us. So I do apologize ahead of time if I don't get to every question. If it's a very long, detailed answer, I'd probably recommend just emailing us. And as a note, we will post the slides and a recording of the webinar probably later today or tomorrow. It'll also be up on YouTube. There are some links in these slides, so please check out our website for a copy of these slides if you want to go ahead and go through them at your own leisure down the road. All right, so what are we going to be talking about today? Well, first, I'm going to talk a little bit about Staties, about our products, Design Expert and Staties 360, as well as introduce the topic of non-ordinary responses, so special models. I'm then going to do a quick, brief walkthrough of 3 situations where you might need special models: binary data, count data, and simulation data. Unfortunately, we only have about 40 to 50 minutes today, so there's really only so much we can touch on each of these topics, but we'll at least, the goal here is so that you at least in the future know how to recognize these problems and where to turn for help. We don't expect anybody to become an expert after this, but hopefully you at least get a general idea of what's going on. And then I'll give some final comments and some resources you can use if you do ever run into this in your own work in the future. So for those of you that are new to Staties, just a brief 1-slide introduction. Staties was founded in 1985, so we've been around for 30, we're getting close to, let's see here, getting close to 40 years here, I guess, by a chemical engineer named Pat Whitcomb, who actually just retired a year or 2 ago. So he was with the company for quite a long time. We're headquartered in Minneapolis, Minnesota. We are a subsidiary. We are owned by Constellation Software out of Toronto in Canada. We are the developers and publishers of 2 leading software packages for DOE, for design and analysis of experiments: Design Expert, and our new software package, which was just released recently and is starting to pick up, Staties 360. And we also provide DOE training and a very limited amount of consulting as well. So this is what most people know us for. So for those of you that are new, welcome. I do want to just touch briefly for a minute or two on our new software. Over the years, Staties has received lots of requests. So we've been known as a DOE company. We only do DOE. However, over the years, we've gotten requests for advanced DOE tools. We've also gotten demand for tools that are not quite old school or strict DOE, things like design and analysis of computer experiments, computing, statistical process control, variability analysis, reliability, and many, many more. our goal has always been to keep Design Expert as simple as possible, because we know 95% at least of our users are engineers, chemists, biologists, people working in the lab. So we really want to keep it simple and user friendly as possible. But the problem, so we've typically tabled requests for advanced features, but at a certain point the demand was simply too great. So we did release Statis 360 about half a year ago. It's essentially a pro version of Design Expert. So it contains a full copy of Design Expert software. So if you're using Design Expert and you're happy with it, you don't need to change. You don't need to buy anything else. However, the first release of Statis 360 also contains some of our most highly requested advanced and adjacent DOE features. So things like space filling designs, Gaussian process models for zero error data. So these are one of the types of models I'm going to be talking about at the end of the presentation today. Python scripting, so if you want to automate processes, transfer data easily between multiple software packages, use Python packages, we do provide that utility in Statis 360. And then coming soon this spring, we'll have a report generator where you could generate reports that update in real time, Excel import and export. So a lot of people will go between Excel and our software and they want it to be easier, and that's coming soon, and then a few more. So these are just kind of some of the big ticket items. So last slide on this. Going forward, Design Expert will continue to be targeted towards engineers, formulators, and others working in R&D. And remember that Statis 360, our new product, contains all of Design Expert. So again, if you're happy with Design Expert, you can keep using it. And going forward, Design Expert will contain all of the easy to use bread and butter techniques, but the more highly advanced non-DOE technical and computational features will only go into Statis 360 for the sake of keeping Design Expert as simple as possible. And some of the things that are coming in the coming years are measurement systems analysis, multivariate analysis, more scripting and computing capabilities, possibly reliability, and more. So this is just a quick 5-minute preview. If you'd like to take we do have a free trial available on our website. So go ahead, if you'd like, you can feel free to sign up for the trial and give it a shot. So with that, why don't we jump into the main topic of today's webinar. So start with a preview of kind of what's going on. Why do we care about these special models? What's a non-ordinary response? Well, in many industrial experiments, you set up the DOE, you collect the data, and then you analyze the data, and then you might iterate on it. There might be more steps and so on. Typically, when you analyze the data, you use something called ordinary least squares regression. So for those of you that have ever clicked on the ANOVA tab in Design Expert, ordinary least squares is used to generate that model. And for any of you that have taken our workshops or have a deeper knowledge of model fitting, you'll know that this ordinary least squares, the standard assumption is this. This is the math version. But what really intuitively what this means is that when you set your factors and you do a run and you measure data, and let's say you reset your factors and you do the same run and you repeat it again and you keep repeating it, when you look at all of those replicates, they should be approximately bell-shaped. And the variability throughout your entire design space should be roughly the same. So that's what we mean by y follows a normal distribution with variance sigma squared. It means that you should have roughly bell-shaped data at each point in the design space and constant variability. And typically we would write the model as y equals x beta, where y is the response vector, x is your actual design and your factor settings, and beta are what we call the model coefficients. So ordinary least squares tries to find the best coefficients for the given experimental design, x, and the measured response is y. And the estimates of beta are found on the ANOVA in the coefficients tab. So if you've ever looked at these coefficients, these are what we call the ordinary least squares estimates. And remember, so here's kind of what's going on. So for those of you that are new to OLS, let's say we just had a one-factor experiment. We have our factor x, which we set here. We have our responses Y, which are plotted here. So you can see the red points are the data points. So this is just a simple one-factor experiment. And what OLS tries to do is it tries to find this blue line here. Tries to find essentially the intercept and the slope that best fits these red points. Now, of course, it's not going to go through all of these red points, but it tries to find the equation of a line where roughly the points on average are as close to that line as possible. That's what ordinary least squares essentially tries to do. When you see the model equation in the ANOVA in Design Expert or States 360, that's how those coefficient estimates were generated. So hopefully hopefully the illustration makes this a little bit easier to comprehend. Now, in some situations, however, ordinary least squares should not be used. So remember what I mentioned just 2 slides ago is that ordinary least squares, it requires continuous data and it requires bell-shaped error with constant variance. You're not always going to get that. So we'll look at 3 alternative modeling methods today. And of course, there are more, but I'm going to go through 3 of the common ones and just mention a few more at the end of this webinar. One is logistic regression. So if anybody has ever did a run, and the only thing you measure is whether something passes or fails, or an animal survives or dies, or something meets specification or it doesn't meet specification, that's called binary data. And we use something called logistic regression to model that. If you've ever, and this is one that's often new to people, if you've ever measured a count, so something that's like 0, 1, 2, 3, 4, 5 within theory that has no upper limit, you might want to consider using Poisson regression because it may give you a better fit than using the standard ordinary least squares regression. And I'll just briefly touch on Gaussian process models because these aren't super common, but people may still want to be aware of them. These are for simulation data. And these are, as I said, these are only 3 of the common scenarios, and there are many more. So with that, let's jump into logistic regression for binary data. Okay, so as I discussed on the slides beforehand, in many cases, and I'd say maybe most cases, you're going to have what's called a continuous response, and you can analyze it using ordinary OLS, ordinary least squares, no problem. And a continuous response is one that in theory can take any value. You may not be able to measure it to infinitely many decimal places or even 5 decimal places, but in theory, if you go by the textbook, it could take any value in some feasible range. So let's say you set your factors of time to 20 and temperature to 300, and you just do a bunch of replicates here. This is what you really want the data to look like to use ordinary least squares, if you just fix the factor settings and do replicates there. So you can see it's not perfectly continuous, but it's bell-shaped, and there's lots and lots of different values here. However, in other cases, you may be forced to deal with a binary response. So this is a response that can take only one of 2 outcomes. So let's say you're doing an experiment where you set the pressure to 200, and then you do the run, and you measure whether something passes or fails. And then you maybe reset the pressure again to 200, and you see if it passes or fails. Sometimes it's going to pass, sometimes it's going to fail, and a way to summarize that is to to graph out the proportion of passes and fails, which have to sum up to 1. Now remember, this isn't a batch where you're looking at a proportion. This is you're doing a run and you measure 0 or 1. You're not making a batch of 100 parts under some settings and then counting the proportion. This is a 0 or 1 for each independent run. So either the pig dies or it doesn't die, and then you move on to the next pig. It dies or it doesn't die, and so on. So some very common examples of binary responses. In quality engineering, you almost always are going to be dealing with pass-fail data. In pharma, some subject either survived or it didn't survive. In medicine, the disease is present or the disease is absent after taking some medication. In marketing, online, somebody either clicked on an ad or they didn't click on an ad. That's 0 or 1. In food, the dough either rises or it doesn't rise. In experiments, you may have both continuous and binary responses. And just as a note, a binary response is often considered to be a categorical response because it's really a category. It's 0 or 1 is what we use mathematically to represent pass-fail, but it could be a yes or no, it could be a blue-green, it could anywhere where there's two outcomes. So here's just a simple one-factor example. So this is an example where, let's say, we did about 60 runs at five different factor settings, and these were all done independently. So this is like really let's see here. We have 39, 48, 56. So we have 56 total runs here that were done at 5 different factor settings. This was not 5 runs. This is 56 runs here. And if we plot the data, it looks something like this. You can see that at the low level of the factor, everything failed. We got all zeros. As we increase our factor a little bit, we get one success out of a total of 8. So 1 success, 7 failures. And as you increase your factor to the upper limit, you see that you end up getting almost all or all successes, all ones. This is what the logistic model looks like. It looks like an S-curve. Ordinary least squares will not generate something that looks like this. In fact, if I did fit an ordinary least squares model, here's what this is going to look like. So you can notice if I just fit a straight line to this data, notice how I get the straight line going below 0 and going above 1 here. These are numbers that just don't work with probabilities. Also, the fit just isn't very good. I mean, it's a linear fit. Now you could say, well, I'm going to fit a cubic model. Then I end up getting a similar situation where here I'm going over 1 and here I'm going below 0. So these probabilities really don't make any sense. Also, if you were to compare the error bars, you'll see that they're widely different because logistic regression assumes a 0-1 response. OLS assumes a continuous response. In general, a binary response gives you much less data. It's either 0 or 1. So here's just a one-slide introduction to logistic regression before we do an example here. Logistic regression overcomes the issues that OLS suffers from when analyzing binary data. Here's what the logistic model looks like, and I know this is maybe a little bit math heavy, but essentially what we're trying to model is the probability of observing a 1 at each point in the design space under factor settings. So some key points to take home here. And this is a typical S curve, so it looks something like this, where it has a lower bound of 0 and an upper bound of 1. Logistic regression models a 0 or 1 response. When you look at the predicted values, they must be between 0 and 1, and they represent a probability. It's a very flexible model and widely used in industry. You can get some really, you can make this look like a bell if you wanted to, that has a 0 or 1 limit if you fit a quadratic model. And it's available both in Design Expert and States 360. And the good news is you don't need to know all of this theory and math to be able to just use it and get results from it. So I think this is best demonstrated with an example. Okay. An aircraft, this is an aerospace example here. Now this is one that I got several years ago. It's a little bit, they sanitized it a little bit when they gave it to me. So it's not quite probably exactly what they did, but it should be representative enough of what they ended up doing. So an aircraft fastener manufacturer wanted to study the ability of a new fastener to withstand different loads. So 2 factors were varied. So first of all, the load on the fastener going from 2,000 to 4,000 PSI, and the thickness of the fastener from 1 to 5, and they didn't give any units. So I don't know if this is millimeters or if this is just some sort of score, but it went from 1 to 5. And what they did is they tested 8 fasteners at 9 different load and factor combinations. Now they tested one fastener at a time. So they took a fastener, they applied some load to it. They took a fastener of a certain thickness, applied a load to it, and then measured whether it failed or not. That's all they had. And what they wanted to do is to see kind of how load and thickness interact to affect the probability of a fastener failing. Each of the fasteners was an independent run. So these were not batches of 8 used to calculate a proportion. So it's not like they put all 8 of them from a batch and then tested them simultaneously. This is one at a time where they had independent replicates. So I think this is probably best shown with an example in States. I'm going to use States 360 for this. And hopefully you're able to see the software. And I already have the data in here to save us some time. So I'm going to go ahead and zoom in a little bit to make this a little bit bigger. And you can see that if I go through this, I have a total of 72 runs. You can see that, for example, for run 1, I took a fastener with a thickness of 1, I applied a load of 4,000 psi, and I saw whether it failed or not. This one failed. You can see that load of 2,000 here at run 7, a thickness of 5 didn't fail. So this is how we went through and we tested these. So what I'm going to do is I'm going to go ahead and start the analysis from scratch here and click on my response here. Now you'll notice that States 360, it sees that you have all 0, 1 data. And what it does is it actually, by default, suggests special model of logistic for binary data. So if you see this, this is a hint that you should probably use logistic regression. If you absolutely wanted to use OLS or this linear regression, you can toggle here where it says linear regression. But we're going to use logistic regression, and you can choose whether you want to model the probability of failure or the probability of success of getting a 1. So let's go ahead and start the analysis. What I like to do is I like to use auto select here, starting with the quadratic model, and use forward. So you could see that when I use the auto selection to build this model, it's very similar to building an OLS model. You can see that it puts in load, thickness, and the interaction between the two. When I look at the ANOVA, I basically get an ANOVA that looks kind of similar to what I had before. I still get p-values, I get some r-squareds here, I get some goodness of fit tests, and I get my coefficients in that equation. For the sake of time, I'm going to move over to the model graphs and show what the 3D surface looks like. So here is the probability of a fastener failing. So you could see that the fasteners are most likely to fail in this red region over here. They're least likely to fail in this region over here, where it looks like thickness is high and load is low, which makes sense intuitively. If I look at the contour plot, this is what I end up getting here. I could see that, for example, if we wanted all of our fasteners to have, let's say, I'm going to add a contour here. Let's say a 95% chance of survival, I would probably need to be in this red region. So they would need to be, whoops, let me move out a little bit. So what this would tell me is, let's see here, edit this contour. Let's make this one 95%. Set contour value of 0.95. So if I wanted my fasteners to have a 95% chance of survival, and of course we probably would want it to be a little bit higher, but this was just the first pass of an experiment they did. They would need to be rated for, they would need to be rated for a load of at least, let's say 3,500, and they would need to have a thickness of, I have this backwards. So the highest probability of failure is in this bottom red region. So if I want to have, let's say, a probability of failure of less than 0.5, I would need to be in this region over here. So basically, high thickness, low load are the best, which is something that we expect intuitively. Now, what I can do is I can reanalyze this using OLS to see what I would have gotten if I really wanted to. I can click on analysis here, the plus button, and simply add a new analysis and reanalyze fail. And what I could do is I could call this fail OLS. And I'm going to use linear regression for this. So if I start the analysis, what I'm going to do is I'll try to use the same auto select here. It gives me the similar model. I get my usual ANOVA here. But then if I look at the diagnostics, you can see that these are clearly problematic. This normal plot of the residuals is not very good. These residuals versus predicted look very bad. So, I mean, I should see that in theory, this is not very good. But if I look at my model graphs here, if I look at something like the 3D surface, I could see that in this red corner here, I'm getting probabilities of failure that are all greater than 1. It actually looks like in this case, OLS doesn't do too terrible, but if I compare it to the logistic fit, it looks like the logistic fit in general is much better, even just going by the goodness of fit tests and looking at the graphs here. So hopefully that gave you a little bit of a taste of kind of what logistic regression is all about. And for the sake of time, I'm going to go ahead and close this and move on so that we don't run out of time here. Let's fire PowerPoint back up. So that was a demo of logistic regression. So logistic regression, again, is used when each independent run of the experiment generates a 0 or a 1 response here, each independent run. If you are measuring a proportion, so you set your factors and you make a batch of 50 and you measure the proportion, you might be able to, you would use OLS in that case, possibly with the arcsine square root transform to stabilize the variance. Question we always get is how many runs? Well, sizing a design for binary data is trickier than for continuous data because there's a lot more going on. The problem with binary data is a lot of times the higher probabilities have different properties than areas of the region where you have low probabilities. So there's more variables that affect the precision and power of the design under a logistic model. In general, we found that DOEs for binary data require anywhere from 2 to 10 times as many runs as for continuous data. And this is still somewhat of an active research question, so we don't have the exact answer just yet. But typically, we also recommend iterating. So build a design that's feasible, collect the data, analyze, look at your confidence intervals. If they're too wide, maybe you might want to add a little more, some more follow-up runs, and so on. We do have a free webinar here that I gave, I want to say 2 years ago, which takes these last 8 slides that I talked about binary data and talks about it for a full hour. So if this is something that's of use, if you like it, please check this webinar out. When we post this presentation to our website, you'll be able to just click on this link. So also, if you just go to our YouTube channel and search for binary, it should be the only webinar that pops up. So with that, why don't we move into the next case, which is Poisson regression. So this is count data. And this is something that people a lot of times don't even realize they're doing. So a count response is something that's often measured in industrial experiments as well. Here is just a handful of, some of the ones that we've seen over the years. The number of defects on a metallic surface. So somebody's making a piece of sheet metal. It could be any surface, and it's never going to be exactly perfect. And they simply count the number of defects on the surface, or the number of solder defects on a circuit board. The number of hits on a web page, that's a count. Colony forming units for an antiseptic formulation, where they count simply how many of these bacterial colonies form, and many more. So notice that to determine whether you have a count or not, first of all, it has to take the value of 0, 1, 2, 3, 4, obviously. And in theory, there's usually no upper limit. I mean, a website could, in theory, get 10 trillion, 100 trillion hits. Of course, practically, there's probably some high values that are never likely to get hit, but in theory, if you go by the textbook, there should be no upper limit. The big caveat is that count data has the property that the variation of the data increases as the expected count goes up. So if you're running a process that's expected to get lots, high counts, in generally the variability is going to be much larger than a process where you end up having low amounts of counts. Now, this is not always necessarily true, but it's usually the case. Counts have a tendency to have more spread as the expected counts go up. Ordinary least squares assumes bell-shaped data and constant variability throughout the design space. So therefore, it's not always the best option for modeling count data. Here's just one example that I pulled out from my many that I have of some count data that I reanalyzed using ordinary least squares. This is the diagnostic plot, the residual versus predicted. Remember, this is one where we like to see constant variance throughout the space. In this example, you have a clear megaphone pattern, which is indicative of non-constant variance. So if you end up going with this model, what ends up happening is your p-values will likely be incorrect. They may be too high or too low, so you might end up with coming to the wrong conclusion. Here's just a one-page intro. So Poisson regression assumes that each run at the factor settings has a Poisson distribution, which looks something like this. These are a couple different Poisson distributions with different averages. So the orange one is what a Poisson distribution looks like with an average count of 1, clearly not bell-shaped here. You could see if with an expected count of 4, this is what the Poisson distribution looks like. And as the counts go up, they do tend to look more bell-shaped. So the model takes the form something like this. Y is equal to the log of x transpose beta. And maximum likelihood is used instead of ordinary least squares to find these unknown coefficients. And these coefficients, again, just like in the OLS, just like in the logistic case, are reported in the ANOVA tab in Design Expert and Statis 360. You don't necessarily need to know all of this theory. As long as you're using the right tool and know what the conclusions to make, you should be in good shape. So once again, let's look at an example, a quick example of counts. So this is a slightly more complicated example. It's a mixture example. It's an antiseptic that's being formulated with 8 ingredients. 4 of the ingredients actually are fixed, and 4 of these ingredients are varied. Excuse me. And the total needs to sum up to 100. So why don't we go ahead and look at Statis 360? Let's take a look at how we would do this. So this is an example that's actually in our tutorial data. I chose this to save some time, but this is our Poisson regression tutorial. So this is the experiment that they ran. They did 20 runs, 20 formulations of this antiseptic. The gray ingredients are not changing, and these first 4 components, 1 through 4, are varying. And what they did is they simply counted the number of colony forming units. So here are a couple different, let's go ahead, and what we'll do is we'll go ahead and analyze this using Poisson. Now there's 2 options. There's Gaussian process, which we'll talk about next, and then there's Poisson. So I'm going to go ahead and start the analysis. I'm going to go ahead and do an auto select here, AICC forward, to see what my model looks like here. Okay, now this is a fairly, here's what my 3D surface looks like. Okay, you can see that component D is over here. I can only plot 3 components at a time. And this is what the model looks like. So this model actually looks fairly similar to what an OLS model would look like, but we can go ahead and plot the OLS model. So for example, one thing we could look at is we could look at that 2-component plot here. Let's go ahead and look at what happens if we just used linear regression to analyze this. So once again, I'm going to go ahead and use forward selection. So I get a slightly smaller model in this case. Okay, and when I look at the same 2-component plot here, So here's one thing I wanted to illustrate is if I look at the Poisson fit here, let's go to the 2-component here. You can see that these intervals are much narrower than these intervals here. And this is simply because I'm using essentially the correct analysis tool. Now, one thing you could do if you wanted to get around this is you could take the square root transform, or you could take a log transform. But in my experience, I would much rather just use the right tool. Also, with a square root transform, you could still get negative predictions. So in general, I just like to use Poisson. So if you go to this analysis we did here, you could see that it's under special models. And this will only be available if the data follows the correct form. So in other words, if you have counts. All right, so that was an example of Poisson regression. So hopefully if this is new to you, you've got kind of a general idea of what's going on here. And so just to wrap this section up, so Poisson regression is used as when the response is being analyzed as a count. Ordinary least squares might work okay in certain situations for count data, but in my experience, it's just safer to use Poisson regression instead, because then you don't have to worry, oh, this is one case where it may not work. And here is a webinar just on the topic of count data and Poisson regression. So it's right here. Available on our YouTube channel, on our website. If you look at count, if you just type in count data on our YouTube channel, there should be exactly one webinar on this that we gave, I want to say earlier this year or last year. So with that, I want to move into the last case, which is Gaussian process models. And this is for simulation data. Now, this last case is somewhat specialized. Not everybody does simulation data, so I don't want to spend too much time on it. But I do want to introduce it so in the future, if you happen to do a simulation, you may realize this. Now, this is something that in my experience, people often don't know that simulation data should be treated differently, and then they end up using ordinary least squares and they don't get a model that fits great. But these experiments are heavily used in certain industries. So I've seen it in medical devices, aerospace, a whole number of industries. In a simulation experiment, a computer program takes some inputs, your factor settings, and what it does is it generates or simulates a response using some simulation software or code that you may have written. And often these simulations might be very, very time intensive. The big caveat here is that if you repeat a simulation under the same factor settings, it will produce an identical response because it's a deterministic process. There is no error. And people will often ask, well, why don't I just simulate everywhere in the design space? And the answer is if it takes a day or a week or even a month to get to do a single simulation, it's not feasible to do that. So a simulation experiment is just like a normal DOE essentially, where you can't test at every point in the design space. You need to select a small design, and then you fit a model to try to interpolate or approximate the response everywhere else in your design space. Ordinary least squares is typically not a great tool to analyze this type of data. Now, Gaussian process models, I'm not going to go into the math here. I think they're best explained by using a picture. So here's a one-factor experiment. Here is one run that I did. Here's another run. Here's another run, and so on. So you'll see that the black line is the model. The model goes through each of my data points. Now, normally this would not be ideal. However, because we know we have no error, if I set the time to 40, plug that into my simulation and get the output, I know it's going to be exactly equal to this value here. So I want my model to perfectly predict my experimental data because I know that data doesn't have any error. However, Gaussian process models also use essentially a weighted average. That's kind of the intuitive way to explain it, to interpolate between your design points here. And then you'll get confidence intervals as well. And notice that the confidence intervals go down to 0 at the design points because we know we have 100% confidence at the design points. So this is really the best way, I think, to look at them. If you've ever done non-parametric regression or a low-S smoother or something along those lines, or a nearest neighborhood average type of thing, nearest neighbor weighted average, Gaussian process models are, in general, the intuition is similar to that, where to get these predictions here, what you're doing is you're essentially taking a weighted average of this response, and all the other responses here. And you're going through your entire design space and interpolating. So that's how you generate the model here. If you have a process that has very, very low error, like a physical experiment in the lab that has almost no error, you could certainly use Gaussian process models as well to fit the data. So it's not necessarily just for simulation experiments, but if there's almost no error, you might be able to get away with this as well. It might be a better fit than ordinary least squares. So here is one example. And this one is came out of a book that I liked. So a simulation was run to determine the expected throughput of a process based on a specified warm-up time. So what they did is they wrote this complicated simulation software to simulate what would happen with their process, how much of this material they can process based on a given warm-up time. Now, there was no way that, apparently, if they wanted to do this as a physical experiment, it was just totally not feasible. It would take too much time, waste too much material. So what they did is they basically simulated this. And then after they found their ideal conditions, they verified 1 or 2 actual runs down the road. And I believe their goal was to hit a throughput of at least 8. I believe that was their goal. So they wanted to figure out what's kind of the lowest what warm-up time would they need to hit a throughput of 8? Or sorry, 8.5 here. Okay. So last demo of the day is our one-factor Gaussian process model. So I'm going to go to States 360, which I ended up closing out of. So I'll go ahead and reopen that. Let's go to one factor. So here's that data that I just showed you in the PowerPoint presentation. So what I did is I analyzed this using both ordinary least squares and a Gaussian process model. So I'll start with the Gaussian process model. Let's see here, let's go here. So you'll notice that this is for 0 error data. This is the only special model that's available. I'll go ahead and start the analysis. I'll calculate my smoothing parameter, and I'll go ahead and look at the model graphs. And this is essentially the best fit. This is more or less that graph that I showed you before. So if I wanted to figure out where can I get at least 8.5, what I could do is I could simply draw a horizontal, I could draw, let's see here, a reference, whoops, not that. Remove the reference line. What I'm going to do is draw a horizontal reference. And I could see that I get 8.5 at about here, roughly. I could use the optimization if I really wanted to and figure out exactly what time I would need to set. But I need to be in about the 80-minute warm-up time here. If I go and I analyze this using ordinary least squares, first of all, it suggests a linear model. So if I look at my model fit, this is what the model, let me delete this reference line. Here's what the model looks like. So you could clearly see that this straight line isn't going through all the points. It looks like there's still error here, and the confidence intervals are enormous because this method doesn't take into account the fact that there's 0 error. If I really wanted to, I could try to fit, some people, what they try to do is they try to fit like a 5th order model and use an auto select. Let's see if this even works. And I don't even think this is going to work, but I could try to fit a 4th order model and see what that looks like. I mean, that kind of looks okay, but I'm still not going through the points. And my confidence intervals here are absolutely enormous. I mean, they're at the point where this is, I don't have much confidence in this model at all. So let's take a look here at some final comments and conclusions. So hopefully this gave you a little bit of an introduction. We do have, as I said, webinars on each of these topics. We do training on each of this. We have white papers. So today we looked at three alternatives to ordinary least squares regression. So logistic regression for binary data, Poisson regression for count data, Gaussian process models for simulation and low error data. These are just a handful of the alternatives for non-ordinary responses that are out there. Some other things you might run into is quantile regression. So if you're looking at measuring, you want to model the median or you want to model the 99th percentile, you would use quantile regression. Penalized regression, weighted least squares regression, and many, many more. There's only so much we can talk about in 45 minutes here. And here are some resources. So if anything that I said got you thinking, here are some resources for further information. So we do have a Studies Academy. We have live public workshops that touch on some of these topics. My general suggestion is go to our official YouTube site, and you can see and you could dig into these topics a little bit more. And finally, we do have a whole bunch of case studies and white papers on our website, some of which deal with binary and count data. So when we post this to our website, you can go ahead and click on any of these links, but they're pretty easy to find. If you go to our YouTube channel, it's really easy to find our videos, and same thing with our website is right on the front page. You can click on case studies, white papers, academy, workshops, training, it's all right there. So I want to thank everybody for joining me this morning or this afternoon or this evening. Once again, I don't think I got any questions during the talk, during the webinar, but if you do have anything that comes to mind, you can feel free to email me directly here. So I want to thank everybody for taking the time to join me. Hopefully you found something useful in here. And again, we don't expect anybody to be an expert after just the 45-minute crash course, but this is more just of an FYI so that you're aware of what's going on. So thanks again, and goodbye now.